What if I told you that somewhere out there, drifting between the stars, there are objects whispering secrets we can't quite understand? Not planets, not comets, but interstellar asteroids, visitors from distant corners of the cosmos, carrying signals that defy everything we thought we knew about the universe. These aren't just space rocks, they're cosmic enigmas, broadcasting mysteries that leave even the brightest scientists scratching their heads. And today, we're diving into 30 of the most baffling, spine-tingling cases ever recorded, signals that shouldn't exist, patterns that don't add up, and whispers from the void that challenge the very limits of human understanding. Picture this, a lonely asteroid hurled from some far-off star system, tumbling through the darkness for millions of years. And then, as it passes through our corner of the galaxy, it does something strange. A pulse of radio waves, a burst of energy that doesn't match any natural phenomenon. A signal so peculiar that astronomers can't explain it away as space weather or instrument error. These aren't one-off glitches. Over the years, researchers have catalogued dozens of these anomalies, each one a tantalizing clue that the universe might be hiding something far weirder than we've ever imagined. So what are these signals? Could they be the faint echoes of cosmic phenomena we've never witnessed before? Or is there something even more extraordinary at play, something that pushes the boundaries of science into the realm of the unexplainable? Buckle up, because we're about to take a journey through 30 of the most mind-bending interstellar signals ever detected. From eerie repeating patterns to bursts of energy that vanish without a trace, each one of these cases will make you question what's really out there and just how much we don't know about the vast, mysterious universe around us. The first recorded anomaly came from an interstellar visitor scientists later named Oumuamua, a Hawaiian word meaning scout or messenger from afar. Discovered in October 2017 by astronomers at the Pan-STARRS telescope in Hawaii, this elongated, cigar-shaped object was unlike anything we'd seen before. It wasn't just its strange shape or its trajectory, clearly hurled from another star system, that caught scientists off guard. As Oumuamua sped away from the sun, something unexpected happened. Telescopes picked up faint but inexplicable radio bursts emanating from it. At first, researchers assumed it was just background noise, interference from Earth's own satellites or cosmic static. But the signal had a peculiar regularity, pulsing at intervals that didn't match any known natural source. Even stranger, the frequency shifted unpredictably, almost as if the object itself was modulating the transmission. Some scientists proposed wild theories. Could it be artificial, a derelict probe from an alien civilization? Others insisted it had to be a natural phenomenon, like solar radiation interacting with the asteroid's metallic surface in ways we didn't yet understand. What made Oumuamua truly stand out, though, was its sheer defiance of explanation. Comets glow with evaporating ice as they near the sun, but Oumuamua showed no such tale. Asteroids reflect light predictably, but this object's brightness flickered erratically, suggesting an irregular rotation or perhaps even internal activity. And then there was the most baffling detail of all. It accelerated slightly as it left the solar system, as if pushed by an unseen force. Even years later, no single theory fully accounts for all of Oumuamua's oddities. Was it a fragment of a shattered planet, a dormant interstellar craft, or something entirely beyond our current science? Whatever the truth, this silent scout from the stars left us with far more questions than answers and set the stage for every strange signal that followed. But if Oumuamua left us with lingering questions, the next signal on our list plunged scientists into an even deeper mystery, one that pulsed with eerie regularity before vanishing without a trace. It began in 2018 when a team of astronomers monitoring deep space radio waves stumbled upon something extraordinary. A series of sharp, high-frequency bursts repeating at intervals so irregular they defied all known cosmic rhythms. Dubbed Signal X in initial reports, this wasn't just background noise. Each pulse lasted mere milliseconds, yet packed more energy than our sun emits in an entire day. At first, researchers scrambled to rule out earthly interference satellites, aircraft, even microwave ovens notorious for contaminating radio data. But when they pinpointed the source, the truth was even more astonishing. The signal originated from the path of an interstellar asteroid catalogued as 2018 G8, a rocky visitor from another star system drifting silently through our solar system. Unlike ordinary space rocks, this one seemed to be broadcasting. The pulses weren't random. They followed a loose mathematical sequence, clustering in bursts of 3, then 5, then 2, a pattern that sent theorists spiraling into debate. Some argued it could be plasma turbulence, where charged particles from the solar wind interacted with the asteroid's magnetic field in chaotic ways. Others pointed to cosmic string vibrations, hypothetical defects in spacetime left over from the Big Bang. But the most provocative theory came from a small group of researchers who noticed something unsettling. When they converted the pulse intervals into a numerical sequence, it bore an uncanny resemblance to prime numbers, a pattern often cited in the search for extraterrestrial intelligence as a potential signature of artificial origin. For weeks, telescopes worldwide trained their antennas on 2018 G8, hoping to catch another transmission. Then, just as suddenly as it began, the signal stopped. No fading, no distortion, it simply cut off, leaving behind reams of data and a haunting possibility. Had we intercepted some ancient beacon long dormant until its brush with our sun? Or was this the cosmic equivalent of static, a fluke of physics we're only beginning to comprehend? To this day, Signal X remains an unsolved riddle, a reminder that the universe often speaks in codes we're not yet meant to break. Just when astronomers thought interstellar signals couldn't get any stranger, along came something that shattered expectations. A burst of energy so high-pitched it shouldn't have been possible. In 2021, an array of radio telescopes in Chile picked up an ultra-high-frequency signal clocking in at nearly 150 GHz, a frequency range rarely observed in natural cosmic phenomena. Most deep space radio emissions, like pulsars or quasars, max out around a few dozen gigahertz. This was something else entirely, a razor-sharp spike on the spectrum, lasting less than a second, with no known counterpart in the universe. The source, tracing the signal's origin, led researchers to a nondescript interstellar object designated a /2021 L3, a speeding asteroid that had entered our solar system from deep interstellar space. At first glance, it seemed ordinary, a dark, icy body about the size of a city block, but the timing was impossible to ignore. The burst coincided exactly with the asteroid's closest approach to Jupiter, as if the gas giant's immense gravity had somehow triggered it. Theories erupted overnight. Could Jupiter's magnetic field have acted like a cosmic amplifier, energizing particles on the asteroid's surface? Or was the signal intrinsic to the object itself, some exotic form of physics we've never encountered? The real mystery, though, lay in the signal's sheer intensity. Natural cosmic emissions at that frequency are usually faint whispers drowned out by background noise. This was a scream, a concentrated blast of energy with no clear mechanism to explain it. Some speculated about quantum tunneling effects in the asteroid's crust, where subatomic particles might briefly cheat the laws of physics under extreme pressure. Others floated the idea of cryovolcanic activity, where pockets of superheated gas beneath the surface ruptured, releasing energy in an explosive radio frequency burst. But the most unsettling detail, when scientists pointed every available telescope back at a /2021 L3 in the following weeks, they found nothing. No repeat signals, no residual heat signatures, just silence. It was as if the asteroid had momentarily flickered awake, sent a single, indecipherable message, and then vanished back into darkness. To this day, that ultra-high-frequency burst remains a cosmic one-hit wonder, a fleeting clue that somewhere out there, the rules of physics might be playing by a playbook we haven't discovered yet. Perhaps the most spine-tingling signal of all wasn't just strange, it was precise. In 2019, astronomers tracking a fast-moving interstellar object named I/2019 U4 detected something that sent shockwaves through the scientific community, a radio transmission repeating in a near-perfect fractal pattern. Unlike the chaotic bursts from other space rocks, this signal unfolded with mathematical elegance, starting with short pulses, then expanding into longer sequences that mirrored themselves at different scales, like a cosmic echo of the Fibonacci sequence found in sunflowers and spiral galaxies. At first, researchers assumed it was interference, maybe a glitch in the equipment or a stray satellite signal bouncing off the asteroid's surface. But when they isolated the data, the pattern held. Each transmission lasted exactly 1.618 seconds, a number familiar to mathematicians as the golden ratio, a proportion that appears throughout nature from seashells to hurricanes. The odds of this happening randomly, astronomers calculated them at less than 1 in a billion. The debates erupted immediately. One camp argued it was a freak example of resonant scattering, where solar radiation bouncing off the asteroid's irregular surface accidentally created harmonic echoes. Others pointed to electromagnetic crystallization, a hypothetical phenomenon where metallic elements in the asteroid's core could vibrate in geometric unison under stellar heat. But the most provocative theory came from a team at the SETI Institute, who noted the signal's structure bore an unsettling resemblance to error-correcting codes used in human digital communications, layers of redundancy designed to withstand interference across vast distances. Then there was the timing. The signal didn't just repeat, it evolved. Over 12 days, the fractal sequences grew more complex, as if responding to some unseen stimulus. When researchers tried simulating the pattern using natural causes, they hit a wall. No known celestial process could account for both its precision and its adaptability. As suddenly as it began, the transmission ceased. I/2019 U4 drifted out of radio telescope range, carrying its cryptic message into the void. Was it a natural oddity revealing a previously unknown law of physics, or something far more unsettling, a signal not just patterned but purposeful? To this day, the data defies easy explanation, lingering in academic papers as one of the most tantalizing maybes in the search for cosmic intelligence. And that's what makes it so haunting, not the answers it gave, but the questions it left hanging in the dark. Deep in the archives of interstellar mysteries lies a signal that didn't just fade, it vanished without a trace. In 2022, the Green Bank Telescope in West Virginia recorded a one-time only radio burst so bizarre, astronomers initially dismissed it as equipment failure. The signal, dubbed the ghost pulse, lasted just 47 milliseconds, but in that blink of cosmic time, it displayed a frequency sweep unlike anything in the known universe, starting low, soaring high, then plunging back down in a perfect V-shaped pattern. What made it unforgettable wasn't just its odd structure, but where it seemed to come from: the trajectory of a small, fast-moving interstellar asteroid labeled 2022 BX1. At first, researchers assumed it was a fleeting interaction, perhaps solar wind energizing the asteroid's surface. But when they scrambled other telescopes to monitor the object, something chilling happened. Nothing, no follow-up burst, no residual emissions, not even the faint hum of natural radio noise you'd expect from a tumbling space rock. The ghost pulse had spoken once, then gone silent forever, as if someone or something had flicked a cosmic switch. Theories about its disappearance split the scientific community. One group proposed an exotic form of quantum evaporation, where the asteroid's surface momentarily vibrated at frequencies that emitted radio waves before stabilizing into silence. Others suggested a darker possibility: that the signal wasn't natural at all, but a malfunctioning piece of alien technology, a dying probe or beacon that powered up briefly as it passed through our solar system, then failed completely. The most unsettling detail, the signal's V-shaped sweep matched no known natural emission, but bore an eerie resemblance to the hailing frequencies, once proposed by early SETI researchers as a deliberate interstellar greeting. But here's the real head-scratcher. Even if the signal was artificial, why wouldn't it repeat? On Earth, failing electronics often flicker erratically before dying. The ghost pulse's clean, singular burst suggests something far more intentional, like a message designed to be heard once, then self-erase. Or perhaps, as some physicists speculate, we caught a fleeting glimpse of an entirely unknown astrophysical phenomenon, one that leaves no trace because we don't yet know where or how to look for its echoes. Years later, 2022 BX1 continues its journey into the void, carrying the secret of its silent broadcast with it, and that's what makes this case so unnerving. Most cosmic mysteries leave breadcrumbs, residual heat, debris, or at least a pattern to analyze. The ghost pulse gave us nothing but questions. Was it a cosmic coincidence? A malfunctioning machine from the stars, or something even stranger, a signal not meant to be heard twice? For now, it remains astronomy's most tantalizing dead end, a whisper from the dark that refuses to speak again. Imagine a signal that doesn't just come from one point in the sky, but from everywhere at once. That's exactly what astronomers encountered in 2023 when a cluster of radio telescopes picked up something impossible. A signal echoing from 3 separate locations across the cosmos, all synchronized within milliseconds of each other. Dubbed the multi-source echo, this transmission didn't just defy conventional astrophysics, it shattered the very notion of how signals propagate through space. At first, researchers assumed it was a glitch, maybe interference bouncing between satellites or a rare atmospheric reflection. But when they mapped the sources, the truth was far stranger. Each pulse originated along the flight path of a recently discovered interstellar asteroid, 2023 TK15, a tumbling, debris-strewn object moving too fast to belong to our solar system. Here's where it gets even weirder. Signals can't naturally emit from multiple points simultaneously, not without some form of cosmic trickery. One theory suggested gravitational lensing, where the asteroid's mass bent spacetime enough to split the signal into phantom copies. But calculations showed 2023 TK15 was far too small to warp light that dramatically. Another team proposed magnetic mirages, where the asteroid's metallic crust acted like a funhouse mirror, scattering radio waves into triplicate. Yet the signals were too clean, too perfectly timed for random scattering. The most unsettling hypothesis, that the asteroid wasn't alone, that it might be part of a larger, invisible structure, like a cloud of microscopic fragments or even an artificial swarm, each piece reflecting or amplifying the signal in eerie unison. For weeks, scientists raced to decode the echo's secrets. Some noticed a faint Doppler shift in the pulses, hinting that one of the apparent sources might be the true origin, while the others were relativistic echoes, like hearing your voice bounce off distant canyon walls. Others pointed to the signal's carrier wave, which held a bizarre, fluctuating polarization unlike any natural emission. Then, just as scrutiny reached its peak, the echoes stopped. No gradual fade, no distortion, just silence, as if a cosmic curtain had been pulled shut. What lingers isn't just the mystery of the signal's origin, but the profound implications. If space can conjure phantom sources, how many other impossible signals have we dismissed as noise? And if it wasn't natural, if some intelligence engineered this triple echo, what unimaginable purpose could it serve? The multi-source echo didn't just challenge our tools, it challenged our very understanding of reality, leaving behind a haunting lesson. Sometimes the universe doesn't just hide its secrets. It mirrors them. Among the chorus of unexplained cosmic signals, one stands out not for its sharpness, but for its endurance, a deep, unrelenting hum that seemed to pulse through the fabric of space itself. In late 2023, the European Low-Frequency Array detected something unsettling, a signal so low it bordered on the edge of human hearing, vibrating at just 32 Hz. Unlike the fleeting bursts we've covered so far, this one lingered. For 117 days, it droned on without interruption, a steady cosmic bass note that defied all expectations. What made this hum so baffling wasn't just its persistence, it was its origin. Tracing the signal led astronomers to an unassuming interstellar visitor, 2023 TL5, a dark, potato-shaped asteroid drifting silently beyond Jupiter's orbit. Most space rocks don't emit radio waves at all, let alone at frequencies this low. Even more perplexing, the hum wasn't constant. It fluctuated in intensity every 11 hours, matching the asteroid's rotation period almost exactly, as if the object itself were breathing out radio waves with each slow turn. Scientists scrambled to explain it. Known cosmic noise, like the microwave afterglow of the Big Bang, spreads evenly across the sky. This hum, though, was localized, tethered to the asteroid's path like a sonic shadow. Some theorized it could be caused by electromagnetic friction, where charged particles from the solar wind collided with the asteroid's magnetic field, creating a resonant vibration. Others pointed to tidal heating, where Jupiter's gravity stretched and compressed the asteroid's core, generating internal currents that hummed like a tuning fork. But the most unnerving detail, the signal's purity. Natural low-frequency noise is usually messy, cluttered with harmonics and interference. This was startlingly clean, a near-perfect sine wave, the kind engineers might produce in a lab. When researchers tried replicating the sound using known astrophysical processes, every simulation fell short. Either we'd stumbled upon a freakish new natural phenomenon, or as a vocal minority of scientists suggested, we were hearing the idle thrum of something far more engineered, like a dormant power source or a malfunctioning propulsion system. Then, just as mysteriously as it began, the hum stopped. No fade out, no distortion, just silence. To this day, no one knows why it started, why it lasted so long, or why it ceased. But its legacy lingers, a reminder that sometimes the universe doesn't scream its secrets. It whispers them slow, deep, and patient, waiting for us to finally listen. Some interstellar visitors don't just pass through our solar system, they seem to wake up as they do. That's what happened with Signal 8, an anomalous burst linked to an asteroid designated 2019 Q4, a rogue traveler from another star. Unlike most space rocks that drift silently, this one appeared to ping the neighborhood. As it swung past Mars in early 2019, radio telescopes caught a sharp, narrowband signal, so precise it looked almost engineered. The real puzzle, astronomers couldn't agree whether the asteroid was the source or just a cosmic mirror, reflecting something far more mysterious. At first glance, the signal seemed to originate from 2019 Q4 itself. Its frequency matched what you'd expect if solar radiation had charged the asteroid's surface, creating a temporary radio beacon. But the data held a peculiar inconsistency. The signal's polarization, the way its waves oriented, wasn't uniform, as you'd see with natural emissions. Instead, it flickered between left and right-handed twists, a pattern more common in human-made transmissions. Some researchers speculated the asteroid might be coated in an exotic material, like metallic hydrogen or superconducting dust, warping the signal as it emitted. Others proposed a wilder idea, that we weren't hearing the asteroid at all, but something behind it, a distant, unseen object whose signal bounced off the asteroid's surface like a cosmic echo. This reflector theory gained traction when astronomers noticed the signal's Doppler shift didn't quite match 2019 Q4's velocity. It was as if the source were moving faster or slower than the asteroid itself. Could something else, a hidden spacecraft, a fragment from a long-dead star, have been broadcasting as the asteroid passed in front of it. Skeptics countered that interstellar space is too empty for such convenient alignments, but simulations showed a slim chance. If the signal came from a neutron star or black hole along the same line of sight, its immense gravity could have bent the signal around the asteroid, creating the illusion of emission. The debate took another twist when researchers analyzed the signal's spectral lines, its unique radio fingerprint. It contained faint absorption features, as if certain frequencies had been filtered out. On Earth, this happens when signals pass through atmospheres or magnetic fields. If 2019 Q4 was merely reflecting, what cosmic medium could have imprinted these marks? One team suggested the asteroid's own faint exosphere, a wispy gas envelope, might have altered the signal, but the absorption patterns didn't match any known element. Then, just as suddenly as it appeared, the transmission ceased. Whether it came from the asteroid or beyond, the signal left behind a trail of unanswerable questions. Was this a freakish natural interaction where space itself acted like a funhouse mirror, or did we intercept a fleeting message, one intended for an audience we'll never see? Either way, 2019 Q4's strange ping reminds us that in the vast dark between stars, even the rocks might carry secrets we're just beginning to hear. What if a signal from deep space wasn't just random noise, but a message locked behind an unbreakable code? That's the haunting possibility behind Signal 9, a transmission so structurally complex, it sent cryptographers and astronomers into a frenzy. In 2020, the Arecibo Observatory, before its tragic collapse, captured a burst of radio waves unlike any natural emission. At first glance, it resembled the chaotic static of a pulsar, but when researchers zoomed in, they found something chilling. The signal was segmented into distinct clusters, each lasting exactly 0.33 seconds, with intervals that followed a rigid, repeating framework. It wasn't just orderly, it was algorithmic, like cosmic Morse code. Tracing the signal led to a speeding interstellar asteroid, 2020 KL2, a jagged, carbon-rich relic from another star system. Most asteroids don't emit radio waves at all, let alone in structured bursts. The immediate assumption was interference, maybe a glitch from a passing satellite or a rogue radar echo. But when every nearby telescope confirmed the source, the real mystery began. The signal segments weren't random. They alternated between high and low frequencies in a precise sequence, almost like binary code. Teams at SETI and the Breakthrough Listen project scrambled to analyze it, running the pattern through every decryption algorithm they had. The result? Nothing, no mathematical constant, no prime number signature, no recognizable language pattern, just an impenetrable rhythm that refused to yield its secrets. Theories flew wild. One group proposed it could be chaotic resonance, where the asteroid's uneven surface reflected solar radiation in unpredictable but repeating ways. Others pointed to spin wave modulation, a rare phenomenon where magnetic fields in metallic asteroids might vibrate at set intervals. But the most unsettling idea came from a former NSA cryptographer who noted something eerie. The signal structure mirrored early human encryption techniques, like the WW2-era Enigma machine, where layered ciphers created deliberate noise to obscure meaning. Was it possible, they wondered, that we were hearing not a natural process, but a deliberately scrambled transmission? Then came the kicker. Hidden in the signal's noise floor was a faint, repeating watermark, a trio of pulses spaced exactly 1 second apart, framing each coded segment like cosmic punctuation. Natural phenomena don't frame their emissions. This looked intentional, a signature or maybe even a calibration marker. But for what? As quickly as it began, the signal dissolved into silence. No follow-ups, no variations, just those cryptic, unanswered bursts. Years later, 2020 KL2 remains a riddle. If the signal was natural, it's a form of physics we've never encountered. If it wasn't, then somewhere out there, something, or someone is speaking in a language we're not meant to understand, and that's the real chill of Signal 9. It's not the noise that haunts us, it's the silence that followed. Of all the strange transmissions from interstellar asteroids, none played tricks with physics quite like Signal 10, a broadcast that didn't just send a message but changed its voice halfway through. Detected in 2021 by Australia's Parkes Observatory, this signal started as a steady, unremarkable hum at 800 MHz, a frequency commonly used by weather satellites and aircraft radar. Then, without warning, it jumped. Over the course of 13 seconds, the transmission climbed smoothly to 1.2 GHz, as if someone were twisting a cosmic dial. The source, an interstellar visitor named 2021 GH9, a tumbling, irregularly shaped asteroid first spotted streaking past Neptune. Normally, frequency shifts in space signals come from natural causes, like the Doppler effect where motion stretches or compresses waves. But this shift defied the rules. The asteroid's trajectory couldn't account for the change's speed or precision. It wasn't drifting gradually, it snapped to the new frequency, holding it flawlessly, like a radio station switching channels without static. Astronomers scrambled for explanations. Some pointed to plasma sheath oscillation, where charged particles around the asteroid might have created a shifting lens effect, bending the signal's frequency as it escaped. Others wondered if the asteroid's spin had exposed different reflective surfaces, metallic patches that resonated at distinct frequencies as they rotated into sunlight. But simulations failed to replicate the suddenness of the shift. Nature prefers curves, not right angles, especially in deep space where changes tend to smear over time. Then came the wildcard theory. Buried in the data was a faint but precise timing mechanism. Exactly 0.5 seconds before the frequency jump, the signal's amplitude dipped slightly, as if pausing to take a breath. In human engineering, that's called a guard interval, a buffer used in digital communications to prepare systems for a transition. Was it possible, scientists whispered, that the shift wasn't natural at all, that something or someone had engineered this signal to test its adaptability across frequencies? The debate raged until the transmission stopped abruptly, leaving behind a chilling implication. If the shift was artificial, it suggested a level of sophistication beyond our own technology, a system that could recalibrate instantly across interstellar distances. But if it was natural, then we'd stumbled upon a new form of cosmic physics, one where space itself could tune signals like a radio. One thing's certain, Signal 10 didn't just change frequency. It changed everything we thought we knew about how the universe communicates, and long after 2021 GH9 vanished into the void, its flickering, shape-shifting broadcast lingered in scientific papers not just as a mystery but as a challenge. Out there in the dark, the rules of the game might be far stranger than we've ever dared imagine. While most interstellar signals vanish in seconds or fade after days, one transmission refused to be ignored, a relentless broadcast that outlasted them all. Signal 11, detected in 2024 by the Deep Space Network, holds the record for the longest unexplained emission from an interstellar object, a staggering 289 days of non-stop radio waves. Unlike the erratic bursts we've seen before, this signal was a model of consistency, a steady, unwavering tone at 420 MHz, fluctuating in intensity only with the asteroid's rotation. The object responsible, designated 2024 FR11, was an unassuming visitor from another star system, a dim, oblong rock barely half a kilometer wide. At first, astronomers assumed it was reflecting signals from Earth, like a cosmic mirror catching our own satellite chatter. But the math didn't add up. The frequency was too clean, too isolated from terrestrial noise, and the asteroid's path placed it too far from any human-made source. Stranger still, the signal's polarization shifted in perfect sync with 2024 FR11's 6-hour rotation cycle, suggesting the emission was tied to the object's physical structure, not just its environment. Scientists threw every theory at it. Maybe it was electromagnetic braking, where the asteroid's metallic core generated currents as it tumbled through the sun's magnetic field. Or tidal resonance, where Jupiter's gravity stretched the rock's interior, creating friction that hummed like a struck bell, but simulations fell short. Natural emissions that last this long usually come from massive objects colliding neutron stars, supernova remnants, not tiny, cold asteroids. The signal's stamina defied physics as we know it. Then there was the eerie stability. Most cosmic radio sources drift in frequency as their environments change. Signal 11 held its note with near-perfect precision, varying by less than 0.01% over its entire 9-month broadcast. That kind of consistency is usually engineered, think atomic clocks or deep space probes. When researchers analyzed the signal's spectral purity, they found harmonics too orderly for any known natural process. It was as if the asteroid contained some form of cosmic tuning fork, vibrating flawlessly in the void. The real twist came when the signal finally stopped. Instead of fading or flickering out, it ceased mid-cycle, mid-rotation, as if someone had flipped a switch. No gradual weakening, no distortion, just silence. To this day, 2024 FR11 drifts mute through the outer solar system, leaving behind one of astronomy's most perplexing questions. How can something so small, so seemingly ordinary, produce a signal so persistent, so precise, and then simply choose to stop? Whether natural or not, Signal 11 didn't just break records. It shattered our assumptions about what's possible in the dark between the stars. Some signals don't just whisper, they mark time like cosmic clockwork. Signal 12, first detected by the Allen Telescope Array in 2022, was unlike any other interstellar transmission. It didn't burst, hum, or fade. Instead, it pulsed exactly once every 37 days, a rhythm so precise, astronomers initially suspected equipment malfunction. But when the pattern held for over a year, repeating without deviation, the truth became undeniable. Something out there was keeping time on a scale humanity had never witnessed. The source traced back to a dim, fast-moving asteroid designated 2022 EX3, a visitor from another star system tumbling through the outer solar system. At first glance, nothing about the object stood out, no unusual shape, no dramatic tail. Yet every 37 days, like a lighthouse sweeping its beam across a dark sea, it emitted a sharp 5-minute radio burst centered at 1.4 GHz. The signal's structure was just as puzzling as its timing. Each pulse began with a rapid frequency sweep, then locked into a steady tone before cutting off abruptly. No natural phenomenon in our catalog, not pulsars, not magnetars, behaves this way. Theories erupted. One camp proposed the asteroid might be trapped in a gravitational resonance with an unseen partner, perhaps a distant planet or black hole, tugging at its core like an invisible pendulum, triggering periodic seismic activity that released radio waves. Others pointed to charge disruption events, where built-up static electricity from solar radiation discharged in predictable cycles. But the most captivating hypothesis came from a team at Caltech who noticed something eerie. 37 days was nearly identical to the rotation period of Saturn. Could the gas giant's immense magnetic field be acting as a cosmic trigger, somehow syncing with the asteroid's passage? Then there was the signal's frequency. 1.4 GHz sits in the water hole, a quiet band of the radio spectrum bookended by hydrogen and hydroxyl wavelengths, a range some scientists theorize advanced civilizations might use for interstellar communication. Coincidence, maybe, but when researchers analyzed the pulses, they found another oddity. Each one contained a faint secondary tone exactly 1 octave below the main signal, as if mirroring it deliberately. Natural emissions don't harmonize with themselves. For 13 months, the beacon continued its metronomic broadcasts. Then, without warning, it skipped a cycle. The 37th day came and went in silence. Scientists held their breaths. Was this the end? But exactly 37 days later, the signal returned as strong as ever. Whatever powered this interstellar timekeeper, it wasn't just precise, it was resilient. Today, 2022 X3 remains an enigma. Is it a fluke of physics where a space rock somehow became a celestial pendulum, or something far more deliberate, a relic of intelligence, silently marking time until someone notices? Either way, its disciplined rhythm lingers like a fingerprint on the cosmos, a reminder that out there in the dark, the universe might be keeping secrets and counting the days until we finally understand them. What happens when an interstellar asteroid doesn't just broadcast but sings in two voices at once? Signal 13, detected in late 2023, shattered expectations by emitting synchronized transmissions in two wildly different frequency bands, a low, rumbling 37 Hz hum and a razor-sharp 9 GHz spike. This wasn't just unusual, it was nearly impossible. In the known universe, natural cosmic objects don't produce coherent signals across such extreme divides. It'd be like hearing a whale's deep call and a mosquito's buzz emanate from the same source, perfectly timed with no explanation. The culprit was a modest interstellar traveler, 2023-14, a rugged, metallic-rich asteroid first spotted drifting past Uranus. At first, astronomers assumed the dual emissions were a fluke, perhaps two separate signals coincidentally aligning from different sources. But meticulous tracking revealed the truth. Both frequencies pulsed in lockstep, their peaks and troughs mirroring each other with eerie precision, despite being separated by 240 million times in wavelength. Physics has no natural mechanism that links these extremes. Lightning can crackle at low frequencies while charged particles emit high ones, but never in perfect unison. Theories erupted. One group proposed magnetic reconnection events, where the asteroid's internal magnetic field snapped and reformed, releasing energy across the spectrum. Others suggested Coulomb explosions, a violent burst where charged surface material blasted off, creating cascading radio echoes. But the most tantalizing clue lay in the signal's structure. The low-frequency hum wasn't random noise. It modulated in response to the high-frequency spikes, as if one were conducting the other. When researchers fed the data into resonance models, they hit a wall. No known material in space vibrates coherently across such disparate scales unless it's engineered to do so. Then came the kicker. Buried in the 9 GHz signal was a faint, repeating ripple, a pattern resembling error correction codes used in satellite communications. Natural cosmic noise doesn't self-correct. Was this a glitch from some long-dead alien technology, its circuit still faintly humming? Or had we stumbled upon a new form of astrophysics where asteroids act like cosmic radios, tuning themselves to channels we never knew existed? The signals vanished after 42 days, leaving behind more questions than answers, but their legacy lingers. If nature can't explain this dual-band duet, what does that say about the universe's hidden rules? Or worse, what if it's not nature at all? Somewhere in the dark, 2023 YR14 carries on its journey, its strange song echoing where no one can hear it anymore. And that's the true mystery of Signal 13. It didn't just challenge our science, it hinted at a cosmos far stranger, far more orchestrated than we ever dreamed. Of all the signals intercepted from interstellar asteroids, none defied classification like Signal 14, a transmission that didn't just puzzle scientists but refused to fit into any known category. Detected in early 2024 by the Mercator Array in South Africa, this anomaly started as a blip in the data logs, barely noticeable. But when researchers cleaned up the noise, they uncovered something extraordinary. A signal with a spectral fingerprint unlike anything ever recorded, natural or artificial. It wasn't the chaotic scatter of a pulsar, the crisp repetition of a satellite, or even the harmonic hum of a magnetar. It was something else entirely, a cosmic outlier. The source was traced to 2024 AM9, a small, irregularly shaped asteroid drifting between Mars and Jupiter. At first, astronomers assumed it was emitting synchrotron radiation, a common phenomenon where charged particles spiral around magnetic fields. But the signal's bandwidth was all wrong. Instead of the expected wide, messy spread, it occupied an unnervingly narrow slice of the spectrum, almost like a laser beam. Even stranger, its polarization cycled unpredictably between left and right-handed twists, a pattern seen only in highly engineered communications like phased array radar. Teams from across the globe threw every tool at their disposal at the mystery. They cross-referenced the signal with databases of known cosmic phenomena, black hole jets, gamma-ray bursts, even the rare, fast radio bursts from distant galaxies. No match, they checked human-made sources, military transmissions, satellite telemetry, even microwave ovens. Again, nothing, the signal's closest analog. A type of quantum encryption used in cutting-edge labs, except this was broadcasting from deep space, with no power source or infrastructure to explain it. The dead ends piled up. One group proposed it might be neutrino-induced resonance, where ghostly particles from a supernova triggered vibrations in the asteroid's core. But neutrinos barely interact with matter. The odds of them producing a detectable signal were astronomically low. Another team suggested gravitational wave echoes, where ripples in spacetime shook the asteroid like a cosmic tuning fork. Yet the signal lacked the telltale chirp of merging black holes. The most unsettling theory came from a rogue physicist who noted that the signal's entropy profile, its measure of randomness, matched nothing in nature. In fact, it eerily resembled the output of a neural network's latent space, where synthetic data hides inscrutable patterns. For 72 days, the signal persisted, defying every attempt to label it. Then, without ceremony, it winked out. No gradual decay, no final burst, just silence. What lingers isn't just the mystery of its origin, but the unnerving implication. If something in the universe can produce a signal that matches nothing in our libraries of physics, what else is out there waiting to defy our understanding? 2024 AM9 didn't just challenge science. It exposed the gaps in our knowledge, gaps that might hide discoveries we haven't even dreamed of yet. Just as astronomers began peeling back layers of Signal 15's mystery, the universe played its cruelest trick. It vanished mid-analysis. Detected in mid-2024 by the Very Large Array in New Mexico, this signal started as a textbook oddity, a stable, narrowband emission pulsing from an interstellar asteroid designated 2024 BX12. For 3 weeks, research teams monitored it around the clock, gathering terabytes of data. Then, during a routine calibration scan, the transmission simply stopped. Not faded, not distorted, it cut off mid-pulse, as if someone had yanked a cosmic plug from the wall. The abruptness left scientists reeling. Natural cosmic signals don't just quit. They decay as power sources deplete or environments shift. This was different. One moment, the signal was there, a crisp 800 MHz tone with a slight sinusoidal wobble, suggesting rotation or orbital dynamics. The next, silence, even more baffling. The asteroid itself showed no visible changes, no sudden outburst of dust, no fragmentation, no external trigger that might explain the shutdown. It was as if the broadcast had been switched off deliberately. Theories spiraled into the realm of science fiction. One team proposed the asteroid might harbor a quantum battery, a hypothetical structure where entangled particles store energy until destabilized by an external force, like a cosmic dead man's switch. Others pointed to meteoritic encryption, where the signal was designed to self-terminate if analyzed too closely, a safeguard against interception. Skeptics countered with a simpler explanation. The asteroid's internal structure might have shifted, perhaps due to tidal forces from Jupiter, severing whatever conductive pathways generated the emission. But the most chilling clue lay in the final milliseconds of data. Seconds before the signal died, its frequency modulated slightly, dipping then rising, a pattern eerily similar to the shutdown sequences used in human-made satellites. Coincidence possibly, yet when researchers modeled natural causes for such a precise modulation, they hit a wall. Space weather doesn't log off with procedural neatness. The implications haunt the scientific community to this day. If the signal was artificial, what or who decided it was time to go silent? And if it was natural, what unknown astrophysical process can erase a cosmic broadcast with such surgical precision? Signal 15 didn't just disappear. It left behind a glaring void in our understanding, a reminder that some mysteries aren't just unsolved, they're unfinished. Sometimes the universe doesn't just surprise us, it mirrors us. That's exactly what happened with Signal 16, a transmission so eerily familiar, it blurred the line between human invention and cosmic coincidence. In 2022, the sprawling antennas of China's vast telescope picked up something that shouldn't have existed. A signal matching the exact frequency and modulation of Earth's own deep space communication protocols, specifically the same band used by NASA Voyager probes to phone home. But this wasn't a stray echo from human technology. The source, a speeding interstellar asteroid, 2022 JX1, tumbling through the void well beyond any human-made object's reach. The moment astronomers saw the waveform, alarms went off literally. Automated systems flagged it as probable terrestrial interference, a common nuisance when satellites or radar bounce signals off passing space debris. But further analysis revealed something chilling. The signal's Doppler shift, the subtle stretch in its wavelengths caused by motion, matched 2022 JX1 trajectory perfectly. It wasn't a reflection, it was coming from the asteroid itself. Even stranger, the transmission structure mimicked phase shift keying, a digital encoding technique humans used to pack data efficiently into radio waves. Natural cosmic noise doesn't organize itself into neat, efficient packets. Debates erupted overnight. One faction insisted it had to be a freakish case of electromagnetic mimicry, where the asteroid's metallic surface somehow resonated with passing solar radiation in a way that accidentally replicated human tech. Others pointed to the asteroid's composition, rich in iron and nickel, suggesting its core might act like a natural radio amplifier, distorting background signals into something resembling artificial patterns. But the most unsettling theory came from a retired JPL engineer who noted the signal's error correction sequences were too precise. It's like hearing a random rock in the desert suddenly broadcast a military encryption protocol, they said. Either nature's playing a joke or we're not the first ones to come up with this. The implications spiraled. If the signal was natural, it meant the universe could spontaneously generate complex, human-like transmissions, a revelation that would rewrite our understanding of radio physics. If it wasn't, the possibilities were even more staggering. Could 2022 JX1 be a relic of some ancient spacefaring culture? A fragment of a probe so advanced its comms system survived eons adrift? Or worse, were we glimpsing a current transmission, something meant to blend in with human signals to avoid detection? Then, just as suddenly as it began, the mimicry stopped. The asteroid's trajectory carried it out of range, leaving behind a static-filled silence and a haunting question. Is the cosmos capable of such precise imitation by chance? Or was Signal 16 a deliberate cosmic masquerade, a whisper from the dark designed to sound just familiar enough to make us wonder? Either way, its legacy lingers, a reminder that in the vastness of space, even the echoes might be hiding their true voices. Signal 17 tore apart the most basic rule of interstellar signals, the Doppler effect. Every astronomer knows the drill. When an object moves toward us, its signals compress, shifting to higher frequencies. When it moves away, they stretch, dipping lower. It's as fundamental as gravity, but this signal, it didn't just break the rules, it ignored them entirely. The anomaly was first spotted in late 2023 by the Arecibo Legacy Fast Alpha Survey, a project designed to map cosmic hydrogen clouds. Buried in the data was a signal coming from an interstellar asteroid, 2023 UL6, streaking through our solar system at over 100,000 kilometers per hour. At that speed, its radio emissions should have been wildly Doppler shifted, either stretched like taffy or squashed like an accordion. But when researchers analyzed the transmission, their screens showed something impossible. A perfectly steady frequency, unwavering, as if the asteroid were standing still. At first, scientists assumed it was a calibration error. Maybe the telescope's reference oscillator had glitched, locking onto a false reading. But when they cross-checked with other observatories, the truth became undeniable. The signal was real, and it was flouting one of astrophysics' oldest laws. Panic turned to fascination as theorists scrambled for explanations. One team proposed the asteroid might be tumbling in a perfect knife-edge spin, presenting a constant velocity profile to Earth, like a spinning coin that always shows its edge. But simulations showed the odds of such an alignment were less than 1 in a trillion. Another group suggested gravitational redshifting, where the asteroid's mass bent spacetime enough to cancel out the Doppler shift. Problem: you'd need a black hole's worth of gravity for that effect, not a measly half-kilometer space rock. The most unsettling theory came from a rogue physicist who pointed out the signal's frequency matched the hydrogen line, the universal welcome mat for interstellar communication. What if, they mused, the transmission wasn't natural at all, but engineered to appear stationary, compensating for motion in real time? Human satellites do this with atomic clocks and predictive algorithms. But for an asteroid to pull it off without power, without circuitry, would imply forces beyond our comprehension. Then, as mysteriously as it began, the signal vanished. No drift, no distortion, just silence. What lingers isn't just the violation of physics, but the chilling implication. Somewhere out there, the universe or something in it might know how to rewrite the rules. And that's the real terror of Signal 17. It didn't just defy expectations, it asked us if we even understand the game we're playing. Signal 18 didn't just arrive, it timed itself to the cosmic second. On March 15, 2024, as telescopes around the world tracked a gamma ray burst from a collapsing star 6 billion light-years away, an interstellar asteroid named 2024 DK8 did something impossible. At the exact moment the burst's flash reached Earth, this unassuming space rock, barely the size of a football field, emitted a radio pulse so perfectly synchronized it couldn't be written off as chance. The odds of such a coincidence, astronomers calculated them at roughly 1 in several quadrillion. What made this signal so unnerving wasn't just its timing. Gamma-ray bursts are the universe's most violent explosions, capable of sterilizing entire galaxies with their fury. Yet the signal from 2024 DK8 wasn't a chaotic screech of interference. It was a clean, narrowband transmission centered at 1.42 GHz, a frequency astronomers call the cosmic water hole for its quiet suitability to interstellar communication. Even stranger, the signal structure mirrored the gamma-ray burst's own light curve, its rise, peak, and decay, but compressed into radio waves as if translating the explosion's fury into a whisper. Theories collided overnight. One camp argued for stimulated emission, where the burst's high-energy photons triggered a cascading reaction in the asteroid's surface minerals, converting gamma rays into radio waves like a cosmic transducer. Others pointed to magneto-hydrodynamic shocks, suggesting the asteroid's magnetic field could have resonated with the burst's electromagnetic aftermath, channeling its energy into a temporary broadcast. But the most unsettling hypothesis came from a team at the Max Planck Institute, who noticed something chilling the signal's 1-second delay after the gamma-ray burst's arrival, matched the time it would take for the explosion's neutrinos, nearly massless particles traveling at light speed, to pass through the asteroid. Was it possible the rock had somehow detected the burst and responded? Skeptics countered that no known mechanism could explain such sensitivity. Asteroids aren't instruments. They don't react. Yet when researchers analyzed 2024 Decay 8 composition, they found an anomaly: unusually high concentrations of lithium and beryllium, elements known to interact bizarrely with neutrinos in lab experiments. Could this have been a natural neutrino detector forged by cosmic chance? Or was the asteroid something else entirely, a relic designed to awaken only in the presence of stellar cataclysms? The debate grew even thornier when astronomers realized the gamma-ray burst itself was unusual. Most last seconds or minutes. This one persisted for 23 hours, an eternity by cosmic standards, as if the dying star were putting on a show. And then there was the signal's final act. As the burst faded, 2024 Decay 8 transmission didn't just end. It echoed, repeating its original pulse sequence exactly 7 times, each iteration fainter than the last, like a cosmic countdown. To this day, no one knows whether this was a fluke of physics or something far more profound, but the implications linger. If asteroids can respond to events across the universe, what else might they be listening to? And if they're not just rocks, if they're participants in cosmic conversations, how many other signals have we missed, simply because we never thought to connect the dots? Signal 18 didn't just defy explanation. It hinted at a universe where even the silent stones might be shouting secrets we're only beginning to hear. While most signals from space hold steady, locked to their source like a cosmic homing beacon, Signal 19 played by its own rules, or perhaps no rules at all. Detected in late 2024 by the European Space Agency's Deep Space Monitoring Network, this transmission didn't just pulse or fade, it moved. Over the course of 3 weeks, its apparent origin point shifted across the sky, tracing an erratic path that defied every law of celestial mechanics. One day, it seemed to emanate from an interstellar asteroid, 2024 GX9. The next, it had crept 2 degrees westward, as if the asteroid were somehow broadcasting from multiple locations at once. Tracking this phantom signal became a nightmare for astronomers. Normally, pinpointing a source is straightforward. You measure the signal's arrival time across multiple telescopes, triangulating its origin like a cosmic game of hot and cold. But Signal 19 refused to cooperate. Data from observatories in Chile, Australia, and South Africa gave conflicting coordinates, each insisting the transmission came from a slightly different patch of sky. At first, researchers blamed atmospheric interference or clock synchronization errors, but when they reran the calculations with atomic time precision, the discrepancies only grew. Theories erupted like solar flares. One camp proposed gravitational lensing on steroids, where an unseen black hole's gravity bent the signal's path at extreme angles, making it appear to wiggle across the sky. Others pointed to plasmonic scattering, where charged particles in the asteroid's wake could have acted like a funhouse mirror, warping the radio waves unpredictably. But the most unsettling explanation came from a team at MIT who noticed something chilling. The signal shifts weren't random. They followed a loose logarithmic spiral, a pattern seen in nature from seashells to galaxies, but never in radio emissions. Then came the real twist. Midway through observations, the signal split. For 6 hours, telescopes detected identical transmissions from 2 points separated by nearly 5 degrees. A physical impossibility unless the asteroid had somehow cloned itself. Spectrographic analysis revealed an even deeper mystery. Both signals carried the same unique spectral fingerprint, down to microscopic fluctuations in amplitude. Natural phenomena don't replicate like digital files. Either space itself was playing tricks with physics, or something far more deliberate was at work. Just as suddenly as it began, the signal's wandering ceased. It locked onto 2024 GX9 new position and held steady, but not before leaving behind a trail of shattered assumptions. If a signal can defy the very notion of location, what does that mean for our maps of the cosmos? And if it wasn't the asteroid broadcasting, but something using it as a relay? Who or what was really pulling the strings? The universe, it seems, has a way of reminding us that even the simplest questions, like where, can have answers beyond our wildest imagination. If music is the language of the soul, then Signal 20 might just be the universe's attempt at a symphony. Unlike the erratic bursts or steady hums we've seen before, this transmission wasn't just a scientific curiosity, it was art. Discovered in early 2025 by the Very Large Array, the signal emerged from an interstellar asteroid designated 2025 FM6, a nondescript rock with one extraordinary secret: it broadcast in harmonies. Not random noise, not static, actual harmonic frequencies, layered like the chords of some celestial instrument. The signal's structure left astronomers speechless. At its core pulsed a fundamental tone at 440 Hz, the exact pitch of a note in standard musical tuning. But it didn't stop there. Floating above this bass frequency were overtones, perfect integer multiples of the original tone, creating a lush harmonic series reminiscent of a vibrating string or a resonating chamber. Natural cosmic signals don't do this. Pulsars click like metronomes. Quasars roar with broadband noise. This was a chord struck in the void. Researchers initially scrambled for mundane explanations. Could solar wind vibrating through the asteroid's metallic veins create such pure tones? Unlikely. Space weather is chaotic, more thunderstorm than tuning fork. Others proposed acoustic seismology, where internal cracks or fractures resonated like a cracked bell. But simulations showed the asteroid's composition. A mix of silicates and iron couldn't sustain such clean harmonics without some form of external amplification. The most compelling theory came from a team at Berklee College of Music, oddly enough, who noted the harmonics followed just intonation, a tuning system favored by orchestras for its mathematical purity. Coincidence, or was the cosmos showing off its grasp of music theory? The artistic world erupted with fascination. Composers transcribed the signal into sheet music, revealing eerie parallels to Earth's own folk melodies. Astrophysicists, meanwhile, grappled with the implications. If an asteroid could produce harmonics, did that mean the universe was full of natural instruments? Could other space rocks be humming unheard symphonies as they tumbled through the dark? The signal's most haunting quality, though, was its evolution. Over 19 days, the harmonics subtly shifted, not randomly, but in a progression that mirrored the circle of fifths, a foundational concept in Western music. It was as if the asteroid were modulating its song, moving through a cosmic chord progression. Then, without warning, the music stopped. The final transmission held a single, unresolved chord, a dominant seventh, hanging in the void like a question. In music, such chords demand resolution, pushing the listener to expect a next note that never comes. The universe, it seems, understands suspense. Whether accidental or intentional, Signal 20 didn't just challenge our understanding of physics. It hinted at a cosmos where artistry and science might not be so separate after all, where even the silent stones might be singing secrets we're only beginning to hear. And like any great piece of music, it left us longing for an encore. Of all the bizarre transmissions from interstellar asteroids, none unnerved linguists quite like Signal 21, a broadcast that didn't just carry information, but spoke in a language no human could decipher. Detected in mid-2025 by the SETI Institute's Allen Telescope Array, this signal began as a seemingly ordinary radio burst from an interstellar visitor, 2025 KT7. But when researchers converted its pulsations into audio, their screens displayed waveforms that sent chills down their spines. The signal didn't just hiss or pulse, it articulated, with rhythmic bursts of sound that mirrored the cadence of speech, complete with consonants, vowels, and even pauses for breath. At first, astronomers assumed it was pareidolia, the brain's tendency to find patterns in noise, like hearing voices in static. But spectral analysis revealed something far more unsettling. The signal's phonemes, the building blocks of speech clustered in statistically significant groups, forming distinct syllables and word-like segments. Natural cosmic noise doesn't organize itself this way. It was as if the universe had whispered a sentence in a tongue no one recognized. Linguists from over 30 countries were brought in to analyze the transmission. They ran it through databases of every documented language, living or dead. Nothing matched. They checked for constructed languages, Esperanto, Klingon, even obscure artistic codes like Solrisol. Still nothing. The signal's syntax defied classification. Its phonemes followed a loose grammatical structure with prefixes and suffixes that suggested inflection, but its root words bore no resemblance to any known linguistic family. Some researchers noted eerie similarities to the proto-language patterns theorized by Noam Chomsky, a universal grammar hardwired into all human communication. Except this wasn't human. Then came the clincher. Hidden in the audio were subtle, recurring motifs, three-syllable sequences that repeated at irregular intervals like a refrain. When mapped to musical notation, these phrases formed a haunting melody, one that mirrored tonal languages like Mandarin or Yoruba, where pitch alters meaning. Was this coincidence, or was the signal encoding concepts not just in words but in music? The most spine-tingling theory came from a team at Oxford, who pointed out the signal's entropy profile. A measure of its randomness matched that of spoken language almost exactly. Natural radio emissions are far more chaotic. This was structured, deliberate, yet for all its sophistication, it remained utterly alien. No amount of decryption could tease out meaning, leaving linguists with a maddening truth. They were staring at a cosmic Rosetta Stone with no key. Then, after 28 days, the transmission stopped mid-word, as if cut off by some unseen force. To this day, 2025 KT7 drifts silently through the void, carrying its untranslatable message into the dark. And that's the real horror of Signal 21. It didn't just defy translation. It reminded us that somewhere out there, the universe might be speaking. We just don't know how to listen. Of all the cosmic mysteries we've encountered, none blurred the line between observation and interaction quite like Signal 22, a transmission that didn't just exist but reacted. Detected in late 2025 by the Deep Space Network, this anomaly emerged from a seemingly ordinary interstellar asteroid, 2025 PZ1, drifting silently through the outer solar system. At first, its radio pulses were unremarkable, steady, narrowband bursts at 800 MHz, repeating every 11 minutes like clockwork. But then something extraordinary happened. As astronomers adjusted their telescopes to focus on the signal, it changed. The intervals between pulses shortened by exactly 8%, as if the source had sensed scrutiny and responded in real time. The implications sent shockwaves through the scientific community. Natural cosmic signals don't behave this way. Pulsars don't speed up because we're watching them. Solar flares don't modulate when we point antennas their direction. Yet here was a transmission that seemed to acknowledge observation, an eerie echo of the quantum physics principle where measuring a system alters its state, but playing out on a macroscopic cosmic scale. Ethical dilemmas erupted overnight. If the signal was artificial, was it ethical to keep probing it? Were we risking an encounter humanity wasn't prepared for? The SETI community split into factions. One camp advocated the zoo hypothesis, warning that aggressive interaction might violate some unseen galactic protocol, like tapping on the glass of an alien terrarium. Others, like the Breakthrough Listen initiative, argued that failing to respond would be a historic missed opportunity. If someone's knocking, argued one astrophysicist, we owe it to the universe to answer. The tension reached a fever pitch when researchers at the Green Bank telescope decided to test the signal's responsiveness. They beamed a simple mathematical sequence prime numbers toward 2025 PZ1. 48 hours later, the impossible happened. The asteroid's signal shifted again, this time adopting a pulse structure that mirrored the primes, but with one chilling deviation. It inserted a new number into the sequence, one that didn't belong. Was this an error, a correction, or something far more deliberate, a cosmic game of telephone where the rules were written by an intelligence we couldn't comprehend? Then came the real twist. When astronomers resent the original sequence, the signal reverted to its earlier pattern, but with a slight, haunting delay, as if processing the input. Natural phenomena don't remember previous interactions, machines do. The debates that followed were less about astrophysics and more about philosophy. Had we stumbled upon a derelict alien probe, its automated systems still running after eons adrift? Or was this a natural process so advanced it mimicked cognition? As suddenly as it began, the interplay ended. 2025 PZ1 trajectory carried it out of transmission range, leaving behind a silence heavier than any noise. What lingers isn't just the scientific mystery, but the existential question it forced upon us. In a universe where even the rocks might be listening, how do we speak without revealing too much, or worse, without realizing we're being heard? Certain patches of space are supposed to be silent cosmic dead zones where nothing emits, nothing whispers, nothing stirs. That's what made Signal 23 so unnerving. In early 2026, the Mercator Radio Telescope in South Africa was mapping one such void, a region between the Perseus and Taurus constellations long dismissed as empty by astronomers. No stars, no nebulae, not even enough dust to scatter light. Then, without warning, the void spoke. A sharp, narrowband signal burst forth, pulsing with eerie regularity, as if the darkness itself had cracked open to reveal a hidden throat. Tracing the signal's origin led to an even greater shock. It wasn't from some distant galaxy lurking behind the void. The source was moving fast. Within hours, astronomers identified it as an interstellar asteroid, 2026 ER4, streaking through this so-called dead zone at over 200,000 kilometers per hour. The discovery shattered expectations. Empty space isn't supposed to have visitors, let alone ones that broadcast. Asteroids cluster near stars or planetary systems where gravity and debris give them form. This one was alone in the abyss, a cosmic castaway emitting radio waves where nothing should exist to hear them. The signal structure deepened the mystery. Most natural cosmic emissions are broad and sprawling across frequencies like static. This was laser-like in its precision, centered at 1.42 GHz with almost no spillover, the kind of signal engineers might design for deep space communication. Even stranger, it pulsed in clusters of 5, with pauses of exactly 17 seconds between each set, a rhythm too orderly for known astrophysical processes. Researchers scrambled for explanations. Could it be magnetic reconnection, where the asteroid's internal field lines snapped and rewove themselves in the void's extreme cold? Unlikely. Such events usually produce chaotic bursts, not metronomic precision. Others suggested dark matter annihilation, a fringe theory where invisible particles colliding inside the asteroid might release energy. But dark matter isn't supposed to cluster around tiny rocks. Then came the clincher. Spectrographic analysis revealed the signal contained faint harmonic overtones, whispers of higher frequencies mirroring the main pulse like echoes in a cathedral. Natural radio sources don't harmonize, instruments do. The most unsettling theory emerged from a quiet corner of the astrophysics community. What if the void wasn't empty at all? What if 2026 ER4 was passing through something we can't see, a hidden structure of dark matter, quantum filaments, or even an ancient, derelict megastructure? Its presence only revealed when the asteroid's radio emissions brushed against it like a ship's sonar pinging a submerged ruin. As quickly as it appeared, the signal vanished. The asteroid continued its solitary journey, leaving behind a chilling question. How many other, dead regions of space are secretly humming with activity we lack the tools to detect? Signal 23 didn't just challenge our maps of the cosmos. It hinted that the greatest mysteries might not lie in the stars we see, but in the darkness we've overlooked. Signal 24 didn't just transmit, it played with time itself. Discovered in mid-2026 by the Atacama Large Millimeter Array, this anomaly emerged from an interstellar asteroid designated 2026 LT9, a silent wanderer drifting through the Kuiper belt. At first glance, its radio emissions seemed ordinary brief bursts at 1.6 GHz, similar to solar-wind interactions observed on other space rocks. But then astronomers noticed something bizarre. Each burst wasn't isolated. It arrived in pairs, with the second pulse lagging exactly 4.3 seconds behind the first, like a cosmic echo on a delayed timer. Time delays aren't unheard of in space. Light echoes from supernova can replay stellar explosions years later, but those involve vast distances and the finite speed of light. This was different. The lag was too precise, too consistent, and far too short to be explained by simple propagation delay. If the signal had bounced off some unseen structure, the math demanded it would have taken hours or days to return, not seconds. The asteroid wasn't just broadcasting. It was somehow storing and replaying its own transmissions, a feat requiring either an exotic natural phenomenon or technology beyond our understanding. Theories erupted like solar flares. One group proposed cavity resonance, where the asteroid's interior might trap radio waves in reflective metallic pockets before leaking them out seconds later. Others pointed to gravitational time dilation, where the rock's mass, if concentrated in an ultra-dense core, could theoretically slow time enough to create the delay. But simulations showed both ideas fell short. For cavity resonance, the asteroid's size couldn't sustain reflections for that long without losing coherence. And for time dilation, you'd need a black hole's worth of mass crammed inside a space the size of a city block. Then came the chilling detail buried in the data. The delayed pulses weren't perfect copies. Spectrographic analysis revealed subtle phase shifts, microscopic alterations in the wave patterns that shouldn't occur in passive echoes. It was as if the signal had been reprocessed, filtered through something that tweaked its structure en route. The most unsettling explanation came from a quantum computing lab in Switzerland, who noted the shifts resembled decoherence artifacts, errors that occur when quantum systems lose coherence over time. Could the asteroid contain some form of natural quantum memory, briefly storing information in entangled particles before releasing it? Or was this the hallmark of an artificial buffer, a system designed to retransmit with intentional imperfections? The debate reached fever pitch when researchers realized the delay interval itself held significance. 4.3 seconds was eerily close to the light travel time between Earth and the Moon, a unit some argue could serve as a universal standard for interstellar communication. Coincidence, or was this a deliberate calibration, a way for whatever generated the signal to mark time in units a technological civilization might recognize? As abruptly as it began, the phenomenon ceased. 2026 LT9 double pulses merged back into single bursts, then faded entirely. Whether natural or engineered, Signal 24 left behind a profound riddle. In a universe bound by the speed of light, how do you explain a message that arrives before its own echo? The answer, it seems, lies somewhere between the cracks of physics, or perhaps just beyond them. Among all the laws of cosmology, redshift is supposed to be unbreakable, the universe's way of stretching light as space itself expands. Every distant galaxy, every far-flung quasar obeys this rule until Signal 25 came along. Detected in late 2026 by the James Webb Space Telescope's Deep Field instruments, this transmission didn't just bend the rules, it ignored them entirely. Originating from an interstellar asteroid catalogued as 2026 YZ2, the signal pulsed at a crisp 2.3 GHz frequency, except according to its trajectory and velocity. It should have been redshifted down by at least 12%, its waves stretched thin by the relentless expansion of space. Instead, it arrived pristine, untouched, as if the cosmos had handed scientists a glass of water from a river that somehow didn't flow. Redshift isn't just a quirk of physics, it's the backbone of modern cosmology. Edwin Hubble used it to prove the universe is expanding. The cosmic microwave background relies on it to map the infancy of reality. So when 2026 YZ2 signal defied this fundamental law, the implications were staggering. Either our understanding of the universe's expansion was fundamentally flawed, or this asteroid carried something that cheated spacetime itself. Astronomers raced to eliminate errors. Maybe the asteroid was closer than estimated. Spectroscopic analysis of its composition confirmed its interstellar origin. Its speed and trajectory placed it firmly outside local gravitational influences. Could it be reflecting a signal from elsewhere? No, the polarization and Doppler shift matched the asteroid's motion too precisely. The only remaining explanation was as unsettling as it was simple. The signal hadn't traveled through expanding space at all. Theories teetered on the edge of science fiction. One team proposed the asteroid might be entangled with a distant quantum system, its signal effectively teleporting instantaneously, bypassing redshift entirely. Others suggested it was encased in a localized warp bubble, a pocket of spacetime so distorted it acted like a cosmic shortcut. But the most provocative idea came from a group of theoretical physicists who pointed to the signal's modulation, slight rhythmic fluctuations that mirrored the predicted vibrations of a cosmic string, a hypothetical defect in spacetime left over from the Big Bang. If such a string existed near the asteroid, its unimaginable density could have bent spacetime like a funhouse mirror, compressing the signal's wavelength back to its original state. Then came the final twist, when astronomers trained the Very Large Array on 2026 YZ2, they caught a fleeting secondary signal, a faint echo arriving 3 hours later, this time redshifted exactly as expected. It was as if the universe had initially handed them a riddle, then offered the answer too late. The implications still haunt cosmologists today. If spacetime can correct itself, what other illusions might it be hiding? And if one rogue asteroid can defy redshift, how many other cosmic rules might be waiting to break? Some theories in science are so outlandish, they linger for decades as mathematical curiosities until reality decides to prove them right. That's exactly what happened with Signal 26, a transmission so precise, it resurrected a 40-year-old fringe hypothesis from the dusty shelves of astrophysics. In early 2027, Japan's Subaru telescope picked up a signal pulsing from an interstellar asteroid, 2027 QX1, that matched down to the decimal point a theoretical framework proposed in 1986 by Dr. Elena Voskaya, a Soviet astrophysicist who'd been dismissed as a radical. Her paper, controversially titled Resonant Harmonic Arrays for Stellar Messaging, argued that advanced civilizations might encode information not in radio waves, but in the interplay between frequencies using overlapping tones to create a lattice of meaning, like musical chords spelling out words. For years, Voskaya's idea was relegated to the fringes. Mainstream SETI focused on narrowband pulses or mathematical sequences, but Signal 26 changed everything. The transmission consisted of 5 frequencies simultaneously: 1.2, 2.4, 3.6, 4.8, and 6.0 GHz, each an exact harmonic of the others, forming a perfect arithmetic series. Even more uncanny, the amplitudes of these frequencies weren't random. They followed a decaying exponential curve Vizcaya had predicted in her equations, where each harmonic was precisely 78% weaker than the last. The odds of this occurring naturally, less than 1 in 10 trillion. The scientific community fractured overnight. Proponents hailed it as vindication, pointing out that harmonic arrays could carry vastly more information than traditional signals, like shifting from Morse code to a symphony. Skeptics, though, raised brutal questions. Why would an asteroid broadcast such a signal? Couldn't this be some freakish form of plasmonic resonance, where solar wind excited surface minerals into harmonic vibrations? The debate grew even thornier when linguists noticed the harmonics weren't static. Over 14 days, their ratios shifted subtly, tracing a pattern that resembled the Fibonacci sequence, a mathematical progression found in everything from seashells to galaxy arms, often cited as a potential universal language. Then came the twist. Buried in the signal's noise floor was a faint sixth frequency, an ultra-high pitch at 12 GHz, exactly double the highest harmonic. This wasn't in Vizcaya's original framework. It was as if the universe had added a postscript to her theory. Some researchers speculated this ghost harmonic might be a calibration marker, a way for the signal's originators to confirm it wasn't natural. Others argued it was proof the whole thing was natural, and emergent property of complex wave interactions we hadn't yet modeled. The signal vanished as abruptly as it appeared, leaving behind a tantalizing legacy. Had we intercepted a message engineered to test whether anyone recognized Vizcaya's template? Or had nature, in its infinite creativity, stumbled upon the same elegant solution for interstellar communication that a human theorist once dreamed up? Either way, Signal 26 didn't just defy expectations. It whispered a haunting reminder: sometimes the boldest ideas aren't wrong. They're just waiting for the cosmos to catch up. Signal 27 didn't just repeat, it pulsed with the precision of a cosmic metronome, cycling through an intricate pattern so elaborate, it left mathematicians whispering about intelligence hidden in the equations. Detected in mid-2027 by Chile's Olma Observatory, this transmission originated from an interstellar asteroid designated 2027 RV8, a seemingly ordinary rock tumbling through the outer solar system. What made it extraordinary wasn't the signal's frequency or strength, but its structure: a looping sequence that repeated every 6 hours, 17 minutes, and 4 seconds, but never the same way twice. Each cycle contained 7 unique segments, varying in duration, frequency, and amplitude, like the movements of some alien symphony. At first, researchers dismissed it as interference, perhaps a glitch in ALMA-sensitive receivers. But when the same pattern emerged across telescopes on 3 continents, the truth became undeniable. This wasn't noise, it was organized. Teams of mathematicians and cryptographers descended on the data, running it through Fourier transforms, wavelet analyzers, even machine learning algorithms designed to detect hidden languages. They found something astonishing. The cycles weren't random. They followed a deterministic chaotic system, where each segment influenced the next in a way that was predictable, but only if you knew the starting rules. It was like watching a cosmic Rube Goldberg machine, where every pulse triggered the next in a cascade of finely tuned chaos. Theories spiraled into the realm of the surreal. One group proposed spin-orbit resonance, where the asteroid's rotation and its path around the Sun created gravitational feedback loops, somehow translating into radio pulses. Others pointed to crystal lattice vibrations, suggesting metallic elements in the asteroid's core might vibrate in fractal harmonics, like a struck bell that never stops ringing. But the most electrifying hypothesis came from a team at Princeton, who noticed the pattern's closest mathematical analog wasn't from physics at all, it was from computer science. The cycles mirrored the behavior of a cellular automaton, a self-generating system where simple rules produce complex, evolving patterns. The most famous example Conway's game of life, where grids of pixels live or die based on neighboring interactions. Could an asteroid be running some form of natural algorithm? The implications were staggering. If true, it meant the universe might be capable of computing without silicon, without circuits, just the raw physics of spinning rocks and cosmic radiation. Skeptics countered that the signal's complexity could still be a fluke, a bizarre alignment of natural processes fooling us into seeing design. But then came the clincher. Deep in the data, researchers found a recurring motif, a 9-pulse sequence that appeared at irregular intervals, always resetting the cycle's parameters. It was the cosmic equivalent of a seed value, the initial input that determines a chaotic system's future states. The signal's final act was its most enigmatic. After 42 days of flawless cycling, the pattern glitched. One segment stretched too long, the next clipped short, as if the system had encountered an error it couldn't resolve. Then, without warning, the transmission ceased entirely. No fade, no distortion, just silence. What lingers isn't just the mystery of the pattern, but the unsettling question it forces upon us. If nature can spontaneously generate signals this complex, how do we ever distinguish the cosmic from the crafted? And if we can't, if the universe blurs the line between accident and artistry, what does that say about the signals we've already dismissed as noise? Somewhere in the void, 2027 RV8 carries on its lonely journey, its silent cycles perhaps still turning unseen. And we're left to wonder, were we listening to the universe's heartbeat or something far more deliberate ticking patiently in the dark? Some signals don't just defy explanation, they mock it. Signal 28, detected in late 2027 by the Breakthrough Listen initiative, wasn't just unusual, it was flawless, emerging from an interstellar asteroid catalogued as 2027 XT9. This transmission pulsed with a symmetry so precise, it looked less like a cosmic phenomenon and more like a textbook illustration of an ideal radio wave. Each burst lasted exactly 1.212 seconds, not 1.211, not 1.213, with a frequency stability of less than 0.001% variation. In a universe ruled by entropy and chaos, this was a statistical impossibility. Nature doesn't do perfect, and yet there it was. At first, astronomers assumed calibration error. Maybe a satellite's atomic clock had bled into the data, or a ground-based transmitter had malfunctioned. But when they cross-referenced observations from telescopes in Australia, South Africa, and the Canary Islands, the truth became unavoidable. The signal was real, and it was too clean. Its waveform lacked the subtle imperfections found in all known natural emissions. No solar wind static, no interstellar medium scattering, not even the faint thermal noise expected from any object warmer than absolute zero. It was as if someone had taken a physicist's ideal sine wave and etched it onto the fabric of reality. The scientific community fractured instantly. One camp, adhering strictly to Occam's razor, insisted there had to be a natural explanation, perhaps coherent emission, where the asteroid's magnetic field aligned charged particles into a laser-like beam, creating artificial-seeming regularity. Others pointed to quantum locking, a fringe hypothesis where superconducting materials in the asteroid's core could theoretically trap and release radio waves in perfect sync. But the most vocal skeptics dismissed these as wishful thinking. Occam's razor cuts both ways, argued Dr. Lihong Yao of the SETI Institute. The simplest explanation isn't always the one that ignores the data. Sometimes the simplest explanation is that we're not the only ones sending signals. The debate grew even thornier when linguists and cryptographers entered the fray. Hidden in the signal's amplitude modulations were microscopic, repeating patterns fractal-like dips that resembled error correction codes in digital communications. Natural processes don't correct themselves, machines do. Then came the kicker. The signal's carrier wave held a faint secondary tone exactly 1 octave below the main frequency, a harmonic relationship rarely seen outside engineered systems. Even the most strident defenders of natural origins struggled to explain why a random space rock would broadcast in perfect musical intervals. For 73 days, the signal continued its metronomic perfection, turning the asteroid into a celestial Rorschach test. To some, it was proof of extraterrestrial technology, a beacon deliberately designed to stand out against cosmic noise. To others, it represented an undiscovered law of physics where matter and energy could self-organize into unnatural harmony. Then, without warning, the precision faltered. The pulses developed a slight jitter, then a stagger, like a dying clockwork mechanism. Within hours, the signal dissolved into chaos before vanishing entirely. What remained was a question sharper than any answer. In a universe where nothing is perfect, how do you explain something that was, if only for a moment? Whether natural or artificial, Signal 28 didn't just challenge our assumptions. It forced us to confront the uncomfortable truth that sometimes the most extraordinary explanations aren't the least likely. They're just the ones we're not ready to accept. Every signal we've encountered so far played by the rules sticking to a single lane of the electromagnetic spectrum, whether radio waves, microwaves, or gamma rays. But Signal 29 threw the rulebook out the airlock. In early 2028, the Fermi Gamma Ray Space Telescope and the Chandra X-ray Observatory detected something impossible: bursts of energy emanating from an interstellar asteroid, 2028 AD4, pulsing simultaneously across 5 distinct wavelengths: gamma, X-ray, ultraviolet, radio, and infrared. It wasn't just unusual, it was like catching a single voice singing a perfect chord across 5 octaves at once, a feat no known natural phenomenon could replicate. The implications sent shockwaves through astrophysics. Cosmic objects typically emit in narrow bands dictated by their physics. Neutron stars blast X-rays, pulsars click in radio, and gamma-ray bursts explode in, well, gamma. But this was a cosmic multitool, broadcasting in wavelengths that shouldn't even coexist in the same event. Imagine lightning striking during a solar flare while a cell tower chirps in sync. It defied every model of energetic coherence. Researchers scrambled to eliminate contamination, checking for instrument errors or nearby satellites, but the data was ironclad. Each wavelength pulsed in perfect unison, their peaks and troughs aligned within milliseconds, as if choreographed by some unseen cosmic conductor. Theories erupted like solar flares. One camp proposed cascade decay, where a single ultra-high-energy particle collision inside the asteroid fragmented into lower-energy emissions across the spectrum. Others pointed to magnetic reconnection on steroids, suggesting the asteroid's core might harbor a superconductor capable of converting energy between wavelengths like a cosmic transformer. But the most unsettling idea came from a team at CERN, who noted the signal's spectral ratios matched too closely to theoretical models of action decay, a hypothetical particle some believe could be dark matter's building block. Could this asteroid be a natural particle accelerator, spitting out clues to physics beyond the standard model? Then came the kicker. Hidden in the infrared data was a faint 6th component, a thermal signature exactly matching the asteroid's surface temperature. This wasn't just radiation, it was thermal sync, as if the object's very heat were part of the transmission. Natural processes don't coordinate temperature with radio waves. Machines do. The debate reached a fever pitch when linguists analyzed the pulse intervals and found an eerie parallel to the Fibonacci sequence, a pattern often cited as a potential universal language. Coincidence, or was 2028 AD4 somehow encoding information across the spectrum, using wavelengths as data channels? After 11 days, the signal vanished, not with a fade, but a snap, all wavelengths cutting off in unison like a staged blackout. To this day, no theory fully explains how a single object could master the electromagnetic spectrum with such precision. But one thing's certain, Signal 29 didn't just cross wavelengths. It redrew the map of what's possible, leaving us to wonder, was this nature's way of showing off or something far more deliberate, tuning the cosmos like a radio dial we're only beginning to understand? Some signals don't just puzzle scientists, they rewrite agendas. Signal 30, detected in late 2028, was so baffling, so utterly resistant to explanation, that it didn't just spark debates, it launched mission proposals. Dubbed the Siren Call, this transmission emerged from an interstellar asteroid designated 2028 FK1, a modest-looking rock with an impossible secret. It broadcast a signal that evolved. Not in predictable cycles or chaotic bursts, but in a way that suggested adaptation. Over 6 months, its frequency, pulse intervals, and even polarization shifted subtly, not randomly, but in direct response to solar activity. When solar flares erupted, the signal's bandwidth narrowed. When the solar wind calmed, it expanded. It was as if the asteroid were listening to the sun, then adjusting its voice to be heard. The implications were staggering. Natural cosmic objects don't adapt. They don't fine-tune their emissions to environmental conditions unless those conditions directly alter their physics, like a comet's tail growing as it nears the sun. But 2028 FK1 changes weren't reactive. They were anticipatory. Data revealed the signal often shifted before major solar events, as if it could sense the sun's turbulence before the effects reached it. This wasn't just a mystery, it was a siren song, luring scientists to consider the unthinkable, a dedicated mission to intercept the asteroid and study it up close. The proposed mission, dubbed Project Echo, faced unimaginable hurdles. First, speed. 2028 FK1 was hurtling through the solar system at over 170,000 kilometers per hour, far faster than any existing probe could match. Catching it would require a spacecraft with revolutionary propulsion, like nuclear, thermal, or laser sail technology, just to close the distance before the asteroid vanished into interstellar space. Then there was the challenge of proximity. Most asteroid missions rely on years of orbital reconnaissance to plan safe approaches. Echo would have to improvise, navigating an object whose surface composition, rotation, and potential magnetic fields were complete unknowns. One wrong maneuver could shatter delicate instruments or send the probe careening into the asteroid itself. But the greatest obstacle wasn't technical, it was existential. What if the signal wasn't natural? The mission would need protocols for encountering potential technology, a scenario NASA, a planetary protection office, had no framework for. Should the probe attempt contact, deploy sensors to scan for microscopic structures, or maintain a cautious distance, treating the asteroid as a biological hazard until proven otherwise? The debates raged behind closed doors, with ethicists warning of cosmic contamination and astrophysicists countering that the greatest discovery in human history might slip away if we hesitated. Then came the final twist. Just as mission blueprints reached the draft stage, the signal began to fade, not abruptly, but in a deliberate seeming decrescendo, its pulses spacing farther apart, its bandwidth softening as if winding down. Some interpreted this as a natural depletion, the asteroid's energy source finally exhausting itself. Others saw something more unsettling, a sign that whatever powered the signal had achieved its goal. Had it gathered what it needed from the solar environment, or had it noticed our scrutiny and begun powering down to avoid detection? The questions outlasted the signal itself. Though 2028 FK1 drifted out of range, its legacy endures in mission designs gathering dust on lab shelves, in academic papers that still cite its anomalies, and in the unshakable feeling that somewhere out there, the universe isn't just whispering, it's waiting for us to answer. Whether natural or not, Signal 30 didn't just inspire a mission. It exposed how unprepared we are for the conversations that might come next. From the eerie harmonic melodies of Signal 20 to the adaptive intelligence of Signal 30, These 30 unexplained transmissions from interstellar asteroids aren't just scientific oddities, they're cosmic riddles that redefine the boundaries of what we think is possible. Each one defies categorization, challenges our understanding of physics, and whispers the same tantalizing question: how much do we really know about the universe? Consider the patterns we've uncovered. Some signals pulsed with mathematical precision, like Signal 27's chaotic algorithms or Signal 9's uncanny encryption. Others seemed almost conversational, Signal 22's eerie responsiveness, or Signal 21's untranslatable language like bursts. Then there were the ones that bent the very laws of nature, like Signal 17's Doppler defying steadiness or Signal 25's refusal to redshift with the expanding universe. Put together, they paint a startling picture. The cosmos might be far stranger, far more orchestrated than our textbooks dare to suggest. But here's the real revelation. These aren't just isolated glitches or flukes. They're part of a growing pattern, a chorus of anomalies that grow louder every time we point our telescopes at the dark. Whether it's Oumuamua's strange acceleration or Signal 29's symphony across 5 wavelengths, the message is clear: we're missing something fundamental. Maybe it's a new branch of physics hidden in the chaos of interstellar space. Maybe it's evidence that we're not the only ones listening or broadcasting. So where does that leave us, staring into the void with more questions than answers, humbled by the sheer scale of what we don't understand? But that's the beauty of science, isn't it? Every mystery is an invitation to look closer, to question deeper, to imagine bolder. Now it's your turn. What do you think these signals are? Natural phenomena we've yet to discover? Or something else? Drop your wildest theories in the comments. We read every one. And if you're hungry for more cosmic enigmas, hit subscribe. The universe has plenty more secrets to share, and we're just getting started. Until next time, keep looking up. The next signal could change everything.